Good evening, everyone, and welcome to Unit 1.5, Lesson 7. In this lesson, we're going to look at a new factoring pattern that can be used for very specific polynomials in a pattern that we call the difference of squares. So, just a little bit about the things that we'll learn in this lesson. What we're looking for here is dealing with factoring patterns that have this form, x plus m and x minus m. So what eventually happens here is we're going to look at multiplying these sorts of polynomials together and how it's going to result in a quadratic expression with no linear term. So we'll get a chance to see that. But also, knowing that multiplying this will lose the linear term, ultimately we can work backwards. So if we have a quadratic expression that has no linear term, we want to look at is it in a right form that we can write it as this particular product, and thereby factoring. So that's really what we're going to be looking at in this lesson. So hopefully this one should be a pretty straightforward quickie because we're going to look at one very specific thing. Okay, so a little bit of a warm-up here, and we certainly did this in class if you remember. So find each product without using a calculator. All right. So, for example, 9 times 11. What's 9 times 11? Well, let's see. 9 times 10 is 90. Add another 9. So it looks like this one is 99, right? So this one's 99. Okay. Now, what's interesting about 99 is the fact that what number is it really close to? It's close to 100, right? And so what is 100? 100 is 10 times 10, or 10 squared. But 99 is one less than that, right? So we're going to say that 99 is equal to 10 squared minus 1. That's kind of interesting. What about 19 times 21? Well, 19 times 21, let's see. Well, 19, so 21. 19 times 20 is going to be 38,380. And we're going to add another 19 to that, so that's 399. But wait a minute. 399 is pretty close to 20 times 20, 400, right? 20 squared minus 1. Now, why is that important? How does this 20 compare to the 19 and the 21? It's in the middle. 10 is in the middle between 9 and 11. What about this one? 99 times 101. Well, let's see. 99 times 101. Well, 99 times 100 is 9900. And then we have to add another 99. That's the one part. And so we get 9999. Well, that's close to 10,000, which, take your guess, that's 100 squared minus 1. So here's an interesting pattern. If I have two numbers that I want to multiply together, right, and they're 2 units apart like this, 9 to 11, 19 to 21, 99 to 101, I can take the number that's in the middle between them, square it, and subtract 1. And that becomes the product of those two numbers. So a little bit of why that's important is going to pop up as we go through this unit. Okay, so here's kind of what we started with the very first objective of this lesson. Let's look at a particular product, and that is x plus 4 times x minus 4. Now, we've multiplied things like this in the past, right? We've multiplied plenty of times. So let's actually try this with some distribution, right? X times x times minus 4, 4x, and 4. So let's fill it in the diagram. X times x is x squared. 4 times x is 4x. Negative 4 times x. And negative 4 times 4, careful, negative 16, right? Okay. So if I do this out, well, what happens? it looks like my like terms would be the 4x and the minus 4x, but those cancel out, right? Like this. Those cancel out. And what I'm left with is x squared minus 16. Well, that's kind of interesting because what we have is we have two things that are just the squares. We have the x squared and we have the 16. And so, as we said, there's no linear term. Now, is that the same thing as x squared minus 4 squared? Yes, it is. And how interesting is that? That comes out from the fact that we have the x that's been squared and the 4 that's been squared. Coincidence? Probably not. Now, how would we multiply this without a diagram? Many of you, at this point, you've practiced enough multiplication that you could do this without the diagram. So if you had x minus 4 and x plus 4, you'd multiply, you'd get your x squared, you'd get your plus 4x, you'd get a minus 4x, and you'd get a minus 16. And just like with the diagram, the 2 in the middle would cancel, and you get the same x squared minus 16. All good, right? So it looks like that we have an answer. So when you have one that's positive and one that's negative of the same number as factors, they're going to cancel each other out. And you're going to end up with just an expression with two terms. Well, that's wonderful, but does that work in other cases? So let's look at x plus 4 quantity squared. So in this particular case, I have two copies of x plus 4. We want to know, does the same thing happen? If I change to positive, if I have two copies of a positive 4, will that middle sign change to positive? Well, what do you think? So if I multiply this out, I get the x squared. But here I get a 4x. I get another 4x here. And 4 times 4 is 16. So I do get the 4 squared, 16. I do get the x squared. But what about the middle terms? The middle terms do not cancel out because you don't have the case of one being positive and one being negative. So they don't cancel. Therefore, I have x squared plus 8x plus 16. This is not the same thing. So the answer, is this equivalent to x squared plus 4 squared? No. And that's because in general, powers or exponents do not distribute across parentheses. The only case where it appears that they do is this case here, but even then, this is not really distributing the power across a single group of parentheses like this. So this is kind of a good thing to know, that the 2 does not distribute here across parentheses or really across addition. And that's really the problem here. You can't distribute this power across the addition. Because what happens is you actually end up with a middle term rather than just having the two terms. Now, if we were to write this in factored form, right, we would look at this and we'd ask the question, well, what two numbers add to 8 and multiply to 16? And we'd do this. We'd put the two x's, and we'd say add to 8, multiply to 16. Well, 16, that's 16 and 1. No. 8 and 2. No. 4 and 4. Ooh, those add to 8. X plus 4. X plus 4. And we'd have our factoring. So we can do this in both directions. Okay. But we're really not concerned. This is lesson 6 kind of problems, and so these is more of our general factoring. So what our focus is on this unit is going to be these particular situations where the factors are of opposite sign. You have the same number, but opposite sign, and that's going to cause middle terms to cancel, leaving us with these two terms expressions. So my next question is going to be, how would I know if I wanted to go from this expression back to the factored form? How do I know by looking at this expression that I can do that? It has to do with the 16 and recognizing the fact that it's a square. It's 4 times 4. So notice the way this is written. Notice I wrote it as x squared minus 4 squared. And I didn't write it as 16. And that's because this only works. This whole system that we're going to look at only works when the two things are perfect squares. X squared is a perfect square. It's the square of x. But 16 is the square of 4. And that's really what's most important. So let's take a look at a few other cases of this. Okay, so we're going to go back and forth between factored form and standard form with these particular expressions. So let's look at a few things here. So consider the fact that, once again, the reason why we're looking at no linear term is when you have this sort of expression. You get the minus 10 and the positive 10, right? So if I were to put this into factored form, now I could go ahead and multiply it out, right? X times x times 10. Well, I could do that. But I also know, based on our previous expression, that if I do a minus 10x and a positive 10x, they will cancel out. And just by looking at this expression, I can see that that's going to happen. So I don't even have to worry about the middle terms. And I can just say, what's negative 10 times positive 10? That's minus 100. Okay, so let's continue. Now, there's lots of ways that these expressions can look, but we're going to think about them in the same way. Let's look at the next one. We have 2x plus 1 and 2x minus 1. Well, if we look at the first one, we did x times x and got x squared, right? But what about 2x? What do I get if I do 2x times 2x? I get 4x squared. And if I do 1 times negative 1, minus 1. So do you see how we always get a minus here? Now, how about this one? 4 minus x, 4 plus x. Well, looks like once again I can multiply 4 times 4, that's 16. And the minus x and the positive x, if I multiply those together, I do get x squared. And because one's positive, one's negative, I get minus. So it doesn't matter if the x is on the right or the left. We get similar things. So at this point, we can start looking at some generalizations. And you'll notice here that you see the same numbers coming up again. How 16 we saw before, how we keep seeing ones and things, and that's because those are all what we call perfect squares. So this sort of pattern, which is called the difference of squares, by the way, as we saw on the first slide, the fact that it's a difference of squares means that the numbers involved will always be perfect squares, which means it's like the product of two of the same number. So 1 times 1, 2 times 2, 3 times 3. So let's make a list of what those numbers are. Well, what's 1 times 1? 1, 2 times 2, 3 times 3, 4 times 4, 5 times 5, and so on and so forth. So here's the first bunch of perfect squares, and you're going to see these most often. 121, and the last one is 144. That's 12 squared. You might see some slightly other ones, like 13 squared is 169, but once you get past 12, we tend to not use those nearly as much. Um, these are the numbers that you'll see. So one big key to dealing with the difference of squares is you need a difference. So you need a subtraction. Notice how all of these standard forms all have a subtraction. And you'll need both terms to be a perfect square. So it either involves an x squared, a y squared, or it's going to have one of these numbers in it. So it's going to have a 100, a 4, a 16. Here's 81. Here's 49. Here's 25. So you'll only ever see these numbers. Now, one of the things, as you'll see going forward, is sometimes you'll have a common factor. If you divide out the common factor, then you'll see these numbers. So we'll see how that works a little bit later on. But for now, let's now try factoring. So if I have x squared minus 81, right? What terms are going to multiply to give me the x squared and the minus 81? Well, x squared is x times x, right? Just like with regular factoring. But because we have no middle term, we know that we're going to have two of the same number. And what multiplies to give you 81? 9 and 9. Because 81 is 9 times 9. And that's how you factor it. Just keep in mind, again, this factoring pattern works for these particular difference of squares. So let's do a bunch of them out. What about the next one? So 49, well, we know that's 7 times 7. And y squared, so plus y minus y. 9z squared, well, 9 is 3 times 3. Z squared is z times z, right? So 3z plus 4 minus 4, because those multiply to give you negative 16. And no matter what, the problems don't really get much harder than that, just recognizing the numbers. So 25t squared, well, 25 is 5 times 5. Plus 9, 5t minus 9. So the reason for the t is, well, there's a t squared, right? And that's how it works. And if we go and we multiply it out, again, you'll see linear term vanishes. And, oh no, fractions. Really? Fractions? Ugh. Actually, fractions are not bad. When you're dealing in squares, fractions are very good. And that's because of the way that fractions and powers work. So remember we said before, if we look at the previous slide, we said that powers do not distribute across addition, right? Well, they distribute across multiplication and division because exponents are defined from those. So what if I had 2 squared? What's 2 squared equal to? 4, right? And what's 5 squared equal to? 25. So what is 2 over 5 squared? Well, that's just going to be 4 over 25. 2 times 2, 5 times 5. And that works because squaring it means I'm multiplying it by itself. So how does that work for this one? Well, we're going to do much the same thing. C times C is C squared, right? Minus and plus, so default minus. And now 2/5 squared is 4 over 25. Just like that. And here we don't have to worry about fractions. So, same thing. So even with fractions, the fractions have to be composed of these numbers in order to work. So you'll see 49 over 16. Well, here's 49, here's 16, right? So what will this factor into? Well, 49 is 7 times 7, right? 16 is 4 times 4. So we know we're going to have a 7/4 plus d minus d. Again, that's how you get the d squared. So other than just the fractions being composed of two separate numbers, really not any harder. Okay. What about some of these? X plus 5 times x plus 5. Oh, now wait a minute. Hey, didn't we just say that the signs have to be opposite? Well, yes. Now, can we multiply this and put this in standard form? Certainly we can, right? X plus 5 times x plus 5, x squared, 5x, 5x plus 25. Now, one shortcut that you might notice, the more you do this, you start realizing that the linear term, that middle term, is just the sum of these two numbers. Because that's how we look at it when we factor, right? We want to know what numbers add to the middle term. So 5x and 5x is going to give us 10x. So one thing that you could start doing is noticing that you have a plus 5 and a plus 5, so the middle term must be 10. Oops. And the end term's got to be 5 times 5, or 25. Okay, what about this one? X squared minus 6. All right, let's factor that. Oh, now wait a second. 6 isn't on my list. Can we do this? Well, sort of. So this one cannot be factored with integers, okay? So it can't be factored using whole numbers. So instead, what we have to do is we have to think about what multiplies to give us 6. So we're still going to have an x here, right? So we're still going to have, oops, I changed the eraser by accident. There we go. We're still going to have x and x, right? That's still going to give us the x squared. We're still going to have plus, and we're still going to have minus. That won't change. But 6, what squared is equal to 6? Well, you might remember from Algebra 1 that you have an operation that undoes square, and that's the square root. So it turns out what I can do for this one, when it's not a perfect square, you still have the subtraction, but the number given to you is not on this list. You have two choices. One, you could see if you can pull a GCF out, because sometimes you can divide by 2 or 3 and arrive at a number on this list. But here, they don't share a common factor. So now you look at the 6 and said, well, I can't break it down into two smaller numbers, so the best I can do is root 6. Okay? So one simple trick that you can do, if this number is not a perfect square, you could just slap a root on it and do, so if it's like 17, I would do x plus root 17, x minus root 17. So you could do that too. All right, now this one. X squared plus 100. Okay. So once again, it's not a minus sign, right? So you would need two numbers that multiply to 100. Well, what are some numbers that multiply to 100? Well, you have 10 and 10, right? Well, let's multiply to 100, but would they cancel out a middle term? Like if you had x plus 10 times x plus 10, would they cancel out a middle term? No, they won't. So, that's not right. What if I did minus signs? Because negative times negative is positive. Well, they still won't cancel out. The only way to get them to cancel is to have one positive and one negative. But then that won't exist. So what now? In a question like this, we say cannot factor. This particular expression cannot be factored using the numbers that we know. So in this particular case, this expression is already in the simplest term that it can be written in. So there's a lot of different words that we can use to represent this. Some people say like cannot be factored. A good math word for this that you sometimes hear is the term irreducible. That's kind of an interesting word. You probably haven't heard that word before. Um, we don't need to use that one here, but that is one common word that can be used to represent a problem that cannot be factored anymore. Um, the problem, though, is uh, there are other ways that we can deal with this expression. So I would rather just simply say that we cannot factor it, at least using the tools that we currently know. All right. So that's really kind of a breakdown of the difference of squares method. Okay. So here's a whole kind of big list of some other ones. Oh, some of these, right, are the ones that we knew. There's my root 6, and that one not possible to factor. So I'd rather, instead of saying not possible, I would just simply say cannot factor. And it's already in the simplest term possible. So, you know, I would just say it a little differently than that. And here's the ultimate formula. If you have an expression composed of two terms, where the two terms have a difference and they are both perfect squares, then they can be written in factored form using the square roots of both of those numbers. And the reason why it works, as I've said all lesson long, is because you have a plus b and a minus b that causes the middle terms to cancel out. Okay, so from that, we can look at lots of different expressions like this. So again, just kind of quickly going through these as well. We're not going to spend too long on this because, again, by this point, hopefully you get used to recognizing them. So x squared, right? X times x. What times what gives you 64? 8 times 8, right? Is this a difference of squares? Yes, because it's a subtraction, two squares, and we know they're both perfect squares. So plus 8 minus 8. Okay. Difference of squares? 9 and 16 check out. X squared, y squared checks out. So 9, that's 3 times 3, so 3x plus, now you'll get a 4y here because 4 times 4 is 16. And so you'll have 3x minus 4y on the other side. So again, same numbers, just change the sides. How about this one? Difference of squares. So 9 times 9 is 81. 1 plus, 1 minus, and 25z squared, that's 5z, 5z. Just like that. And they really don't get any harder than that. Okay, what about this one? Is this a difference of squares? Oh, got the plus sign. So no. So this one cannot factor. The sum of squares does not factor. So anytime this sign is a positive where I have two terms, not going to factor. All right. We can keep doing this all day long, right? And no matter what, it's pretty much the same stuff. How about 121? Well, that's one we haven't seen a whole lot yet. That's 11 times 11. So that's 11m. Now over here, I have two sets of variables, right? I have an n squared and a p squared. Well, looks like we're just going to have np plus np minus np. Just like that. What about over here? Uh-oh. 2 and 72, those aren't perfect squares. Oh, am I going to have to do that square root stuff? Oh, wait a second. So, thing with factoring, right? Let's go back to our first couple lessons on factoring. If we remember all the way back in lesson 5, we should always look for a GCF first. So we look at this question and say, do these numbers share a common factor? They do, 2. So what I can do is I can divide both of these numbers by 2, the common factor. So what am I left with? I'm left with w squared minus 36. And is 36 on my list? Absolutely it is. That is totally a perfect square. But remember, we are factoring, right? So this 2 doesn't just vanish. We put the 2 out in front, like this. So the 2, as we did with our GCFs, we always wrote it in front, and we put our leftover expression in parentheses. Now, does this factor? Is this a difference of squares? It absolutely is. We get W plus 6 and W minus 6. What happens to the GCF of 2 then? Nothing. It comes along for the ride. And so, because it comes along for the ride, now we have the GCF and the factor. And what we've now done is we've broken this expression down into 3 parts. The 2, the plus 6, and the minus 6. And if I multiply that all together, I do in fact get my minus 72. So this totally works. So case in point, and actually while we're on this one, if you wanted to check your work and remultiply this back to this expression up here, okay, my suggestion is to do it backwards from the way we factored it. So start by multiplying out the parentheses first. Start by doing that. Once you get that answer, then multiply by 2. Because the one thing that is a very common thing a lot of people will do is they'll try to take the 2 and distribute it to all the numbers. No, can't do that. The 2, turns out, only distributes to a single set of parentheses. And this is kind of a fringe rule that you don't hear much about. If I wanted to remultiply this, this 2 only multiplies to the first set of parentheses, not to both. So because that can be hard to remember, I don't like to do it that way. I like to multiply the factors out first here. Because if you do this and get your W squared minus 36, then you have a single factor, and you can multiply by 2 without a problem. So I would rather do it that way. But this is what we call completely factored. When we have an expression that requires multiple factor steps, like a GCF and then an expression, we call that completely factored because I've had to do multiple steps, and now I know I'm totally done. Okay, so last thing I'm going to share with you guys, just some expressions here. We can also solve equations using difference of squares, right? So, for example, say I have the expression x squared minus 100 equals 0. So I want to solve for x. Now, there's a few different ways you could do this, but because we have a difference of squares, let's go ahead and factor it. And it factors into x plus 10 and x minus 10 equals 0. Why? Because 100, 10 times 10, right? Now, once I know that, remember that from a previous lesson, we could say, well, x plus 10 equals 0, this 0 product property, and x minus 10 equals 0, x equals negative 10, and x equals 10. Now, again, if you don't need to write out all of those steps, you don't have to. If you want to go from here straight to the answers, you can. But here, just again, showing you why those answers exist. But again, these equations really only work when you find the solutions if the expression equals 0. And so I strongly suggest doing that. Okay? Like, look at this one. This one says that you have equals 11. So in order to factor to solve, the equation should equal 0. So let's subtract 11. So I get 4x squared minus 1 equals 0. Okay, well, can I factor this? Is this a difference of squares? Sure is. 4, so that's 2x, right? 2x plus 1 minus 1. So again, we can break it down. 1 times 1 is 1, right? Okay, so once again, 2x plus 1 equals 0, 2x minus 1 equals 0. And again, this works because the expression equals 0. So one of these pieces has to be 0. All right, so now we solve, and if we solve, we get x equals negative 1/2. And this one, solve, 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 x equals positive 1/2. Difference of squares will almost always create two answers that are the same but opposite sign. So either x equals 1/2 or a positive 1/2. All right, what about this expression? Now again, if you're solving using difference of squares, right? Again, don't be tempted to try to divide both sides by 25 because it looks like you could, right? But does 81 really divide by 25? Not really. It's not a whole number. You can make a fraction. But again, let's set the equation equal to 0. So subtract 81. They're not like terms. And we can write it in a factored form. Now, is it a difference of squares? Notice I always ask myself that question first. Yeah, 5 times 5, 9 times 9, right? So 5x plus 9, 5x minus 9. And now we can solve from here. So we get, 5x plus 9 equals 0. So we subtract the 9. We divide by the 5. We get x equals 9/5 or positive 9/5. You're going to get the same thing on the other side when you solve. You'll add the 9, divide by 5. Again, two of the same answer, but opposite sign. All right, and that's how it works, folks. So again, solving these sort of quadratic equations are really best done when the equation equals 0, because when it equals 0, oftentimes you can perform a factoring, and it makes much smaller expressions to solve. All right, and that's pretty much it for the kinds of problems that we'll see here. So here's a bit of a lesson summary. Again, this is in your notes. That kind of dictates a little bit of the summary of how we determined that these expressions were factorable. But notice here what they did is, one trick that we could do is we could add a middle term of 0. It's kind of an interesting thought. But notice that you'll never be given this as an expression. On your papers, you'll never see x squared minus 0x minus 9. You'll always see it as x squared minus 9. So you can think about it, though, as, what multiplies to negative 9 but adds to 0? 3, negative 3. Okay? So the big key to success here is just making sure that you recognize when that difference squares occurs and how to factor that from there. And then also recognizing when you don't use this. So remember, this expression here, x squared plus 9, no can do. And that's because it's not a difference of squares. So recognize expressions that work and also recognize expressions that don't work. All right. Hope this has been enlightening to you, but I will leave it off here. So have yourself a lovely evening, and I will see you in class.